Here is the counterintuitive part of industrial robotics right now. The biggest limiter is not strength or even dexterity. It is trust, proven through measurement, governance, and boring operational discipline. Cobots already work in many factories, but mostly in tightly constrained tasks. They succeed where the workspace is standardized, the tooling is consistent, and the edges are controlled. In those settings, the hard part is less about the robot's raw capability. It's about integration, safety assurance, and keeping performance steady over time. Humanoids, by contrast, are still not in mass industrial deployment as of 2026. Public demos focus on walking, balance, and simple pick and place. Those are real achievements, but they do not answer the questions that determine scale. Can the machine run a long duty cycle day after day? Can it be maintained by ordinary technicians? Can you build a credible safety case for a shared human space? Shared space safety is the first gating discipline to internalize. A robot near people is not just a moving arm with a safe speed setting. You need collision avoidance that works in messy reality. You need proxemics, meaning how close it gets, how it yields space, and how legible its motion feels. Predictability matters, because humans coordinate by reading intent in body movement. If a robot's path looks erratic, people will step wrong, hesitate, or overreact. What makes this difficult is that safety is not only objective, it's also perceived. Perceived safety changes behavior, compliance, and willingness to work nearby. That's why measurement instruments for human perception are so important. Since the late 2000s, researchers have built repeatable scales for perceived safety, along with related constructs like likability and perceived intelligence. Those scales are not soft, they are tools for commissioning, training, and accepted gates. A practical implication follows. You should treat perceived safety like you treat vibration on a turbine. Measure it at baseline, measure it after changes, and act when it shifts. If workers feel less safe after an update, intervention patterns will change. They may avoid the robot, take slower paths, or disable features. Throughput can drop even when the robot is technically improved. The second gating discipline is mobility, especially localization in imperfect environments. Many industrial sites are hostile to clean sensing. Dust, glare, steam, reflective surfaces, repeating geometry, and partial occlusions are normal. LiDAR registration methods have improved, including approaches that explicitly consider localizability, meaning how well the environment supports confident position estimates. That sounds abstract, but it points to the operational truth. Confidence management is as important as localization accuracy. A system that sometimes becomes uncertain must degrade gracefully. It should slow down, stop, request help, or retreat to a known safe pose. What you cannot accept is abrupt failure. Sudden loss of localization turns a pilot into an incident, and incidents kill programs. Now add a third discipline that often gets overlooked: the interface. Human-robot interaction is not a cosmetic layer. It's a throughput lever and a safety lever. When humans instruct a cobot, ambiguity is a real hazard. Gesture, speech, user interfaces, teach pendants, and demonstration all have failure modes. The right question is not, is it natural? The right question is, what is the measured command error rate, and how long does training take? Mixed reality methods are now being used to elicit gesture vocabularies for specific task families. The point is to discover what people will actually do, not what designers assume they will do. Then you test those gestures for confusion, collisions in meaning, and edge cases under time pressure. If you change the interface later, even slightly, you should treat it as a safety-relevant update. A new gesture set can create a new class of mistakes. Notice what ties these three disciplines together. Each one demands measurement, change control, and clear thresholds for action. That leads to the fourth discipline, auditability, and it's where many robot programs quietly fail. When something goes wrong near humans, you need incident reconstruction. You need to know what the robot perceived, what it believed, what it decided, and what it executed. If the autonomy stack includes learned components, because the model said so, is not an acceptable explanation. Explainable AI work has mapped taxonomies and limits for explanations, but the operational challenge is more specific. What artifacts help a supervisor decide to override in real time? What logs let an investigator determine root cause within 48 hours? What evidence will an insurer accept? In practice, auditability means you mandate event logs for safety-critical actions. Stops, obstacle classifications, reroutes, near misses, and overrides should all be recorded. Those logs need retention policies and access policies. They also need integrity, because incident data becomes liability data. If you cannot reconstruct incidents, you cannot improve safely, and you cannot scale responsibly. From there, the fifth discipline becomes unavoidable. Fleet governance. As soon as you deploy more than a handful of robots, you are running an Internet of Things system with legs and arms. You need device identity, provisioning, telemetry, monitoring, and update pipelines. You need staged rollouts, rollback plans, and incident response. Without that, a single bad update can propagate regressions across a fleet. This is where strategy leaders should shift their mental model. Stop thinking of robots as individual machines you buy. Start thinking of robot labor as a managed service you operate, with a full life cycle. Software updates are not free improvements. They are change events that require revalidation, especially inside shared human spaces. Process changes in the facility are also change events. Move a rack, change lighting, alter floor markings, or adjust shift routines, and you have changed the operating conditions. That leads to a critical concept borrowed from autonomous vehicles, but applied to industry. Operational Design Domain, or ODD discipline. Every deployment needs an explicit statement of where the robot is allowed to operate, at what speeds, with what payloads, under what proximity rules, and with what environmental constraints. When the ODD drifts, risk drifts. Scaling without ODD discipline is how you accumulate near misses until you finally get a headline incident. So what should you ask for if you allocate capital, set policy, or approve deployment at scale? Ask for a unit of account that matches reality. Useful labor hours delivered. Not peak payload, not maximum reach, not demo videos. Useful labor hours with distributions, not single numbers. Then tie that unit to leading indicators. Intervention frequency, stop event rate, recovery time. Near miss definitions that are consistent and auditable. Pair objective incident metrics with perceived safety metrics, so you can catch problems early. If perceived safety drops, while near misses stay flat, you may be training or interface limited. If near misses rise while perceptions stay calm, you may be accumulating hidden risk. Finally, remember the time horizon. Near-term expansion is real for cobots and standardized work cells. Near to mid-term pilots are plausible for humanoids and mobile manipulators, but only in narrow, explicitly governed domains. Mid-term workforce transition concentrates in facilities that redesign processes for robot compatibility and treat fleet operations as core infrastructure. Farther out, the humanoid form factor may matter less than the institution around it. Certification, insurance, audit, and liability allocation become the true scaling constraints. The memorable line is simple. In industrial robotics, capability gets attention, but governance earns deployment.